Okay, the live stream should be rolling.
Okay. So if we're streaming, I guess I can start the session. Welcome everyone to the second physics session of the day for Varsity Sci. So this is our student panel session. We had Professor James.Many speak this morning, and now we have 6 students to speak about what they've been up to over the summer and some of their interests. So we are going to start off with Georgia Nixon, and she will be speaking on quantum simulation with ultra-cold atomic gases. So I'm just going to hand over to Georgia.
Hi, everyone. My name is Georgia. Today I'm going to be speaking to you about quantum many-body systems, and in particular what I've been looking at during my PhD, which is how we can create new Hamiltonians with the local periodic driving. So I'm working in the group with Dr. Ulrich Schneider in the quantum many-body dynamics group at the University of Cambridge. So just briefly, first off, I'm going to give a whirlwind introduction to quantum many-body physics. So basically, quantum many-body dynamics is the study of systems of many quantum objects and what happens when you have strongly correlated systems. So following from a quote by P. Anderson, more is different, which is a really important concept in quantum many-body systems. So basically, often we can get novel phenomena that cannot be predicted by single particle quantum physics when we have many quantum particles interacting. And so the workhorses of quantum many-body physics are the Bose-Hubbard.
Oh, sorry, we can't see your screen, so could you try sharing it again? I'm sorry to cut you off.
Can you see now? Yeah, great. Okay, so the workhorses are the Bose-Hubbard and the Fermi-Hubbard models, which are essentially toy models to describing many-body systems. So you can imagine that a system of many quantum objects might have a huge amount of degrees of freedom, but it turns out under some certain assumptions, we can simplify the system down to relatively very few parameters. So the firstly being that under the tight binding model, and assuming that we are in the ground state at all times, the ground band at all times, then we can model the system by 3 terms. The first being the hopping between neighboring sites. And so we can say that the energy cost of this we call J. And we can also include an interaction term, which describes the energy cost of two atoms coming close to each other. And we can also account for an on-site energy, which might be the energy difference between 2 different sites. And here we're assuming that we are in the microcanonical ensemble. So the particle number is fixed and we are thermally isolated from our environment. And so the study of quantum many-body systems has been hugely advanced by significant technological advances in the experiments. So particularly, I work in a group where we use ultra-cold atoms in optical lattices. So we have them ultra-cold, we want them around nanokelvin, and this is to freeze out all the thermal degrees of freedom, which we don't want, so that the quantum nature of the system can be explored. We then turn on an optical lattice. So what this is 2 or more retroreflected laser beams which interfere to form a standing wave. And then the neutral atoms then feel a potential due to the AC Stark effect, or the interaction between the atoms and the laser light. And this creates a periodic structure that we can use to probe different Hamiltonians of interest. So these cold atoms and optical lattices provide a huge degree of tunability over, so a large parameter space can be explored. We have no coupling to the environment, no phonons, and all the atoms are identical. So this gives us perfect symmetry and high scalability. So given we have a lot of atoms. So this gives us really unprecedented control and a clean system with which to analyze our systems. So effectively, once we have our lattice structure, we take projective measurements or snapshots of the many body system locally over time. And this allows us to study one of the most fundamental equations in quantum mechanics, which is the Schrödinger equation. So look at the dynamics of the system over time. And so generally numerical methods are available to simulate these strongly correlated systems over time. However, they have serious limitations on system sizes, or we have problems when we try to stretch to higher dimensions, and limitations on the time of the simulation. So the experiment has really opened up the possibility of probing some fundamental questions in quantum physics and other simulation questions. And the Hamiltonians that we use and the timescales that we're interested in gives overlap to many other fields. And so we can probe lots of rich and interesting physics just with these cold atoms and the lattices. One of the main examples of this is condensed matter. So the lattice states that we create with optical lattices can support many different states of matter that look like electronic materials. So this relates to very different fields of physics. So the cold atoms and the lattices versus the condensed matter. But essentially the Hamiltonians governing them can be exactly the same. However, we can read out the results better. We can also probe other areas like high energy physics. We can probe dynamical gauge fields and many computationally intractable problems in high energy physics. We can probe topologically non-trivial band structures, and this provides insight into topological insulators, quantum Hall physics, and general topological order. We can probe quantum thermalization out of equilibrium dynamics, and many other different systems of interest. So essentially what we're doing is taking ultra-cold atoms, thousands of atoms, confining them in arbitrary geometries and different effective dimensions in order to simulate systems of interest. So now I'm going to just talk briefly, more specifically about what I've been looking at, which is how we can use flow-K physics in order to generate new Hamiltonians that we might be interested in. So just a brief introduction to flow-K physics. So, and I'm going to draw on some intuition that you might have from Bloch's theorem. So Bloch's theorem describes a Hamiltonian that is periodic in space. And if we have something that's periodic in space, there are certain things that we can say about the solutions of this Hamiltonian, namely that they are Bloch states, where we have a U of X, which is periodic with the same periodicity as the fundamental Hamiltonian. And then we also have this phase factor, which is position dependent. And so this means that if we translate the eigenstate by a lattice constant A, then we pick up only this overall phase. Similarly, this happens, there's a very similar concept that we can describe, used to describe systems that are periodic in time. So when a system is periodic in time, the solutions to the system are flow-K states, where we have part of the solution is periodic in time with the same periodicity as the underlying Hamiltonian. We call this U of T. And then over time, we have this overarching phase factor as well. So this means that if we look at the system stroboscopically in time over our whole period, capital T, then we're only adding this overall phase factor. And this looks like that the solution is evolving under a new time-independent Hamiltonian G. So really the main points of this are that we start out with a time-dependent Hamiltonian HT, but if it is periodic in time, we can actually describe the system stroboscopically with a time-independent Hamiltonian G. And this time-independent Hamiltonian might have new and interesting features, which are intractable using a time-independent Hamiltonian. So specifically what I want to talk about is what I've been looking at, which is what sort of things can we generate when we locally move the lattice periodically in time. So here's a particular system where we are moving the on-site energy of one lattice site up and down periodically, and everything else is just we have a usual Hamiltonian with bare hopping between sites. And then it turns out that this whole system can be described by a time-independent Hamiltonian, where now we have renormalized tunneling that is local to the shaking via the Bessel function here. And I'll just remind you that the Bessel function goes between positive and negative values. And this means that generally, if we shake a system, we can effectively describe the long-term dynamics of the system with this new Hamiltonian G, where the hopping on either side of the shake has been renormalized. Something that is even more useful is if we were to shake all sites to one hand side of a certain lattice site. And this means that actually the effective Hamiltonian that we generate only modifies one local tunneling. This can be a really useful thing if we want to extend this further to larger systems, and we can generally create different shaking structures within the lattice in order to renormalize different local tunneling elements that we want in order to generate different systems of interest. One system that we have been looking at in particular is something called the Su-Schrieffer-Heeger model, which is what I've given a bit of a representation down below, which is where we can alternate the hopping between J and J prime just by inducing different shakes in the lattice periodically. So that's just a very brief whirlwind introduction to quantum many-body physics, and in particular local periodic driving. I'd like to thank all my collaborators and my group. And are there any questions?
If you have a question, you can raise your hand or you can put it in the chat. Yeah, go ahead, Luca.
Hi, Georgia. Thanks for your talk. I was wondering what kind of theoretical or computational tools you use to model which ones of these kind of scenarios are interesting to look at, and what does that involve?
Do you mean with the experimental system, or with when we use, or generally to sort of initially sort of on a computer to sort of see what things we're going to get?
I guess initially on a computer, and then maybe also on an experimental platform.
So on a computer, there are a lot of, I use Python firstly, and there are a lot of good libraries in Python that we can use to effectively solve differential equations. And we use, which is in order so that we can solve the Schrodinger equation and find this effective Hamiltonian. So in particular, if we take eigenstates of the system, evolve them under this new Hamiltonian, the time-dependent Hamiltonian, and then create how the eigenstates have evolved over one period in time, then we can use those new time-evolved states to reconstruct what the effective Hamiltonian is between when we started and that period in time. Does that make sense? This works very well for one-dimensional systems, and we can extend it to two-dimensional systems. However, it can be computationally intractable when we include interactions. So you'll notice that the sort of systems that I've been modeling at the moment have been non-interacting systems in one dimension, which don't give very many limitations on what we can do. So there's a lot of simulations that we can do on the computer to see what sort of results that we're going to get before we actually do them in the experimental setup, if that makes sense.
Thank you.
I also have a question, if no one else does. So thanks for the talk again. And so you mentioned that you're working in the microcanonical ensemble, right?
Yes.
So I was wondering, because I don't know much about many-body physics, but I've heard about the problem of localization, of thermalization before. When you have systems out of not in thermal equilibrium and then failing to reach equilibrium, I was wondering if you did any work with that, if you have.
Yeah, so that's a really interesting point, but basically what that comes down to the timescales of our system. So when we have a system out of equilibrium, we might get heating of the system, and it turns out with these flow K dynamics, there's something called flow K heating, but what we're interested in is much smaller timescales. So we can effectively say things like we're in the microcanonical ensemble, we're not losing any atoms, we're not adding any sort of heating, because once we get those sorts of effects, these sorts of assumptions that we're making aren't true anymore. You're right.
Okay, thank you very much. I think that's time. So thank you again, Georgia, for your talk. And I think it should be Oscar who's presenting next. Correct me if I'm wrong.
Yes, hello. Can you all hear me? Just to check.
Yes, yeah, we are.
Okay, perfect. My name's Oscar. I'm an undergraduate student, and I'm going to give you a talk about the work that I did as a CERN summer student this summer. So just as a brief introduction, in case you haven't heard of the Large Hadron Collider, it's basically probably the biggest experiment that has ever been built by humanity. It's a 27-kilometer circumference synchrotron, which is a particle accelerator that accelerates protons around and then collides them at a center of mass energy of 13 tera-electron volts. And it's this massive ring here that you can see in the diagram next to Lake Geneva in an absolutely beautiful environment. And dotted around the Large Hadron Collider are a number of different experiments. So there's Atlas over here, which is the experiment I was working on, ALICE, a large ion collider experiment, CMS, the compact muon solenoid. And all of them together are taking data from these collisions and trying to test the standard model of particle physics. So the ATLAS experiment specifically is this massive cathedral-sized detector. The dimensions are here. It's literally as big as a cathedral. And around here, in the middle of this detector, there's the beamline meets, collides, and we get jets of particles that are created, which are then detected in various different detectors that are dotted all around the system. So the problem that we were trying to study was this flavor symmetric quark anti-quark annihilation to form another quark and anti-quark. It's probably the simplest possible process that you can study in quantum chromodynamics, but it offers a lot of information, potential information about the universe, because it allows us to test the standard model to very high accuracy. And so what happens is that when the protons collide, you can get this annihilation process and then a release of another two quarks. Then these two quarks, I don't know if you can see on the top right-hand side, will go on to radiate gluons and radiate other particles and produce these jets, which we then see down here. And these are measured in the detector. And in particular, the measurement that I was looking at was probably the most simple measurement, which is the inclusive jet cross-section, which is where you basically count the number of times that you get jets that are within some transverse momentum and rapidity bins. So the transverse momentum is the momentum component, so that's perpendicular to the direction of the beam line. So in this case, the beamline is, I think it's coming straight on. So the transverse momentum would be sort of the momentum component, any momentum component perpendicular to the straight on direction. And the rapidity characterizes sort of basically the energy and the longitudinal momentum. In some ways, it's related to this pseudo rapidity, which characterizes the angle. So given inclusive jet cross sections, what we want to do is that we want to study the standard model to high accuracy. So we need to have some way to do calculations. Now, using quantum chromodynamics, it's relatively complicated to do any sorts of calculations. But when we've got quarks only, we can do the calculation as a perturbation series using these Feynman diagrams that you might see at the top right-hand corner. But since at the Large Hadron Collider we've got proton-proton collisions, we actually need to take into account the momentum of the individual quarks within a proton. So a proton is in general actually a very complicated composite particle. It's not simply just up, down, and down, but rather it comprises all sorts of virtual quark and anti-quark pairs, which pop in and out of existence at very rapid timescales. And the sort of composition of quarks, and particularly the momentum distribution of all the quarks inside a proton, are characterized by this thing called the parton density function. Now, it turns out that the simplest way that we have the way that we can calculate these cross sections is actually quite simple, thanks to this thing called the factorization theorem in QCD, which tells us that we can calculate the cross sections by calculating first these perturbation theory terms from the Feynman diagrams just for the single quark anti-quark processes, and performing a convolution with these parton density functions. And so doing those sorts of calculations in 2015, the Atlas experiment itself did the calculations and looked at the data and found extremely good agreement over a massive range of orders of magnitude. You can see here, for example, for this rapidity bin, it's spanning from about 10 to the 4 to 10 to the -5 or something. So across all this range of transverse momentum, we're getting extremely good agreement between data, which is the point, and theory, which are the yellow bands. And I myself repeated these same sorts of calculations here using a slightly different program myself. And we see here, again, extremely good agreement over a wide range of orders of magnitude, which is fantastic. Now, in order to really be able to see this in a lot of detail, we can take ratios. And here we see something quite interesting, though, which we couldn't see just from this diagram, which is that the QCD, the ratio of QCD to data is always slightly bigger than 1, which at first sight might seem a little bit worrying. But it turns out that what's going on here is that our calculations have lots of different systematic uncertainties. And so something that I learned over the summer basically was that in high energy physics, they spend a huge amount of time accounting for all the different systematic uncertainties that you have in both the data and in the theory calculations. And here, what I mean by systematic uncertainties is that there are basically different ways that you can calculate the theory. For example, each of these different ones is each of these different points shows a different way that you can calculate the theory using different renormalization and factorization schemes. You can see, for example, that this one completely underestimates the nominal, etc. There's lots of stuff that goes on there. In particular, I was interested in the quark contact interaction, which is a beyond standard model process. I don't really have much time to go into it, and nor do I really know much of the details myself. But in a very similar way to quantum chromodynamics, you can run the same sort of calculations, calculating a perturbation theory, perturbation series, and then taking a convolution with a parton density function in order to calculate inclusive jet cross sections. And from that, we can then plot to see what our contact interaction contribution does relative to the QCD. Now, if we're looking for beyond standard model theory, we want it to only really be important at high energies, because we know that at low energies, or at least energies that we've probed at the Large Hadron Collider, the QCD is a pretty extremely good theory. So it's quite nice that the contact interactions that we were looking at only deviate significantly from QCD at high transverse momentum. So in other words, at high energy. this I don't have time to go over, but these are basically two different methods that we can use to perform hypothesis tests to try and exclude certain models. In particular, we can see that in the previous slide that the contact interaction is characterized by this characteristic scale lambda. And basically, as lambda increases, then the transverse momentum at which the contact interaction becomes important also increases. And the aim of our project was basically to try and establish a limit on which contact interactions could still be explained by the data that we obtained. And doing that sort of thing, we obtain these fairly interesting results. We see that if the two quarks have the same chirality, so they're left-left or right-right, then they, in general, larger energy, and so they have a higher lambda contact interaction, which is excluded. And if you have color octet states versus color singlet states, then again, it's a lower energy, lower limit even. So future work that can be done, there's lots of work. I was only working for about 10 weeks, so barely even got a chance to really dig my teeth into this sort of thing. But there's a lot more data that can be analyzed. You can also use this Python package called PyHF, which will account for the correlations between the systematic uncertainties in a much more rigorous way than the way that I accounted for them. And there are all sorts of other things that we can do as well. We can take ratios of the different cross sections at different center of mass energies in order to reduce the systematic uncertainties in the data and in the theory calculations. And it's possible that in the future, this big future circular collider that the EU is spending $50 billion on might potentially yield some more significant, statistically significant results than what we're able to obtain at the moment. But that's very speculative. Anyway, I'd like to thank you for listening to my talk, and I'd welcome any questions. Thank you very much.
Okay, thank you very much for your talk. Again, if anyone has any questions, either raise your hand or post them in the chat. If not, I was going to ask about if you could go back a couple slides to the one where you have a bunch of uncertainties.
Right. Yeah.
Yeah. What sort of is that like a major variation in methods of calculation, or like how do you get what's such a wide range of different results?
Yeah. So basically, what happens is that we have to calculate that perturbation series. It's done computationally, so someone else wrote some Fortran code that I use.
Okay.
But when you do the calculations, there are these different scales: the factorization scale and the renormalization scale, and you can use those to basically account for where you cut off your perturbation series. Because when you're doing the perturbation series, you have to have a cutoff at some point.
Yeah.
And you can also use this sort of thing to investigate, for example, if the perturbation series diverges, which would then be a very bad thing. But I think that's the whole point of actually this thing called renormalization, which is where I don't really understand it yet. We'll probably cover it this year in part 3. But it's sort of like you have a perturbation series that actually diverges, but then you set an energy cutoff, which is, I think, this renormalization scale μr. And then with that energy cutoff, you can then somehow, using the renormalization group, get some results that are finite rather than diverging.
Okay,
and
that's
somehow, yeah. Okay, great, thank you.
Okay, thank you very much. If anyone else has any other questions, we have 1 minute. If not, thank you very much, Oscar, for an interesting talk. And we can move on to our next speaker, who is going to be speaking on calibrated geometry and gauge theory in dimension 8. So Maksymilian, if you want to take over.
Hello. Thank you for inviting me today. Let me just share my slides. Can you hear it? Can you hear me well and see my slides?
Yes.
Yeah.
Great. So, all right. So, hello again. I'm Max, and in general, I'm interested in interactions between physics and pure maths. And this was the subject of the project I did with Professor Jason Lowthai from Oxford Mathematical Institute this summer. And I'd like to introduce to you calibrated geometry at instantons, which in general show how techniques used in theoretical physics can be used to solve abstract mathematical problems. So for the outline for today, firstly, I'll introduce some maths background for those who are not quite familiar with geometry, then introduce the two subjects in question, and finish off explaining how they are related and why it is interesting. So main objects we work with here are differential forms, which are basically functions of vectors to scalars defined over a curved space, which we formally call manifolds. And everyone has encountered some of them, at least. For example, the Euclidean metric tensor, aka scalar product, where you put two vectors and get a scalar out of some kind, complex or real, or the Euclidean volume form, when you put a few vectors inside and you get the volume of the parallelepiped spanned by them. For those perhaps familiar with complex geometry, a Kähler form is a good example as well. And good objects have operations, and these are no others. Well, the first one is the wedge, we sneak it here, and the volume form, which allows us to link various forms together to form forms of taking in more vector arguments. So in general, if you have a K form and an L form, you get a one with K plus L vector inputs. The other one is the differential, so a sort of generalization of directional derivative when you sum. If you split the form into a scalar part and the basis of vector inputs, you change another vector inputs in the sum by multiplying by the partial derivative in this direction. And this one is closed, so if you apply the diversion twice, any differential forms disappears, which is a bit different from a regular derivative for subfunctions. And the last one is the Hodge star, which allows us to split the space in question into two parts. So we have a K form. The Hodge dual is an n minus K form. So we are able to separate our space into spans of one form and the other, so that we have two disjoint ones. And the wedge and the Hodge dual are designed in the way that in 3D we retrieve the cross product from them. The other piece of mathematical information which might be useful for it is bundles and connections. So bundle in general is an object which is locally a product space, but globally something completely different. So the best example to imagine is the tangent bundle. And we have some kind of manifold, in this case, it's a circle, and we attach vectors at each point. And we can always retrieve the point from the whole structure. And if we go the other way, we retrieve so-called fiber, which are vector spaces. So in tangent bundle, these are just tangent vectors at each point of the manifold. A slightly more abstract notion is the G bundle. So if we additionally add a group action on our manifold, we can attach, instead of a vector space, a orbit of the group action at each point. And when we consider the fibers, these are the orbits of the group function we consider. And knowing that one, having vectors attached to our manifold, we want a way to move them around somehow. For example, if we look here, we have two spheres, and we want to move a vector from the pole to the equator. We can do it in various ways, for example, keeping the angle constant to the equator or to the surface of the sphere. And an object which encodes this kind of behavior is called a connection. It can be encoded as an abstract one form. And depending on the connection, we can always also probe the curvature of the bundle we consider using the curvature to form, which is a tensor related, for example, to Riemannian curvature tensor. So having defined that, we can move on to the more interesting things. Calibrated geometry was invented to probe minimal surfaces and more general submanifolds. Minimal surfaces are those who have extreme volume in their setting. and submanifolds are the same in any dimension. So these are usually described by a second-order PDE, which is not nice because they are usually difficult to solve. So the guys from States, Harvey and Lawson in the 1980s, came up with an idea very similar to analytical mechanics. So instead of a second-order PDE, we try to reduce it to a first-order PDE. And we do it like this. We take a differential form of the same degree our volume dimension is. And we make it closed and bounded in the sense that if we put k vectors inside, it's always smaller than 1, or smaller than any scalar. You can always scale it down if you wish. And the locus where the form actually is equal to 1 turns out to be volume minimizing. This is the main theorem. So it worked, and instead of second-order PDE, solving, for example, for this Lagrangian catanoid formed by the soap film, which tries to minimize the surface, we can go with the first-order one. And a simple example is any bounded form in Euclidean space, because we can always find a plane and it is equal to 1. And also complex geometry, like Kähler forms, produce more intricate examples. So the other piece of interesting theory is the Young-Mills theory. And as many of you probably know, it's the backbone of particle physics and quantum field theory. And it sort of tries to generalize physical fields like electromagnetism, which is the model example. For this, we define a generalized version of energy, the Young-Mills functional, which is the curvature tensor squared and integrated over the whole manifold. And if we apply the principle of stationary action to this thing, we get the Euler-Lagrange equations, which in this special case are called the Young-Mills equations, and take this form using the Hodge star and the differential. And a very interesting solution to those, which I looked at in my project, are anti-self-dual instantons. These are defined by this equation, anti-self-dual because we have a minus and a dual here. And these turn out to be a minimizer of the energy, which is quite a strong condition. So this might seem very abstract, but it's actually might be made on familiar things. If we consider for our G bundle the unitary group of the circle group over the 4D spacetime as a manifold, we actually retrieve the electromagnetism. So notation is not random. A is the full vector of potential, and F is the Maxwell tensor. If we go a step forward and consider a more complicated bundle, a product with special unitary group 2 and 6, we actually get the standard model. So this is sort of the mathematical geometrical description of what we know of physical fields now. And a related concept is called, this is gauge fixing, which in physics means fixing additional degrees of freedom to make the system work. In this case, it's just choosing a particular coordinate system on our manifold for these abstract 1 form and 2 form, which are different kinds of objects. So if we localize it, it's equal to choosing like a Coulomb gauge or Lorentz gauge in electromagnetism, for example. Right, so what's it good for? Well, the geometry of 4 dimensions is really well studied, partly because of the relation to general relativity. And what if we want to go to higher dimension? We have one simple obstacle, just because of the formulation of the definition of instanton, is that this is a 2 form. This as a Hodge dual is 4 minus 2 form, so a 2 form, and the dimensions of the equations work. If we go beyond the dimension 4, now we have an issue because this is a 2 form and this is n minus 2 form. So to even up the ranks of the equations, we need an n minus 4 form to put here. And it turns out that if we take this n minus 4 form we put here to be a calibration, so to be bounded and closed, we actually get a minimizer of the Young-Mills functional. So we not only sort of increase the dimension of our system, but introduce it in a non-trivial way, because those differential forms are very much dependent on the geometry of the underlying manifold we choose. And this is interesting because, as I mentioned, there were multiple cases of using techniques from theoretical physics and pure maths, which were actually quite fruitful in finding new solutions. And Young-Mills theory was one of the most important ones. It allowed people like Edward Witten or Simon Donaldson to find very interesting properties of 4D manifolds in general. And in fact, it turns out that if the same principle works for higher dimensional geometry. So for example, if we take complex manifolds, including Kähler manifolds, or very weird things like exceptional holonomy manifolds, I can explain what these are in Q&A if someone is interested. Using these equations, we can actually extract very interesting things about those manifolds, including manifold invariance, which happen to be quite strong in those cases. So the main message I wanted to convey through my talk is that the interaction in mathematics and physics is not only mathematics used for modeling things in physics, but also techniques which were born in physics are very useful in showing new results in pure mathematics as well. Thank you.
Okay, thank you very much. So does anyone have any questions? Again, raise your hand or type it in the chat and I'll read it out. Yeah, Georgia, unmute yourself.
Hi, Max. Thanks so much for a really interesting talk. I was just wondering if you could go back to where you were defining the vector bundles. Mm-hmm. And I don't know too much about it, but I had heard that when you extend these notions to higher dimensional spaces, there's some really interesting things, like there's the Hopf
vibration.
Yeah, I wondered if you could explain a little bit more about that, or yeah.
Yeah, so thank you for this. Bundles in general interesting because this sort of dual nature, that they are globally something completely different than product manifolds and locally exactly those. And it's they are very useful to introducing new structures of manifolds, just like physical fields, as I mentioned. And the example you mentioned belongs largely to complex geometry. Hopf vibration is used to reduce a dimension of a 3-dimensional sphere in 4-dimensional ambient space into the regular 2-dimensional sphere in a 3-dimensional ambient space. And it's quite unique in its behavior. And it's one of the things in complex geometry that makes the 4D geometry so exceptional. I actually work with in an example like this. I try to construct an instanton on a complex projective space in dimension 8. And there are techniques in dimension 4 when you can reduce it to dimension 3 and analyze everything there and solve the instanton equation using exactly Hopf vibration you mentioned. And I found that it's impossible in dimension 8 because there is no direct analog of Hopf vibration for dimension 8. And in fact, this means that a whole class of manifold which exists in 4D is non-existent in 8D, because this exact method of going from dimension 4 to 3 doesn't work for going from dimension 8 to 7, I think smaller. So this is what is interesting about the geometry of the bundles. Hopefully that answers your question somehow.
Okay, thank you very much. Any other questions?
I have Jacob. Yeah, let's go to Jacob, and then I have one more.
Hi, thanks for the talk. I was just wondering why you chose dimension 8 to study.
Oh, that's a good question. Thank you for this. I don't know if you are somehow familiar with geometry. There is a very strong manifold invariant holonomy, and it's basically, if we consider transporting the vector around the manifold in parallel transport, so-called, and we consider only moving around certain loop based at certain points, we get a set of maps, and these maps form a group. This group is called the holonomy group, and it's a very strong manifold invariant. And the strength is in this, that the thing called Berger's classification is that if a space is not locally a product space and symmetric space, so it doesn't have an inversion symmetry, you cannot flip it inside out. Any manifold that exists is one of these listed here. And the holonomy groups are quite well known. Those are orthogonal and unitary and symplectic groups. And I chose dimension 8, and in particular hyper-Kähler manifolds, because as you can see here, they have a lot of structures. They have 3 Kähler structures, so it's a structure related in complex geometry and symplectic geometry. And in addition those three behave like quaternions. So you can compose them and create, in fact, the whole sphere of complex structures. Additionally, I took dimension 4 because hyperkähler manifolds are necessarily multiple by all 4. And I chose dimension 8, sorry, because now we also have a connection to the spin 7 exceptional holonomy. These two are really weird groups. They do not fit those. Because here there's actually a chain of belonging, because unitary belongs to orthogonal, special unitary to unitary, etc. These two are weird and exist only in dimension 7 for G2 and dimension 8 here. So I chose dimension 8 to firstly check why the dimension 4 techniques do not work. Secondly, because I could have a non-trivial hyperkähler. And thirdly, because it was connected to spin 7. And actually, it turns out that any instanton you define using a special unitary bundle is actually a so-called Hermitian-Young model. So it's related to the Kähler calibration. And it turns out in dimension 8 that the spin 7 calibration from this gives us exactly the same instanton solution. So this is sort of the motivation.
Ah, interesting. Thanks a lot.
Yeah, Jacob's question covered me as well, actually. So yeah, that's fine. Thank you very much.
Thank you.
I think then we can move on to our next talk. So that will be Luca on cooling atoms to almost absolute zero using lasers and magnets. So if Luca, you can take over.
Hi, you can probably hear me, but now you should also be able to see me. Okay, thanks. So yeah, thanks to the organizers for organizing this very interesting conference. And today I'll be telling you something about some of the techniques that we use in our lab to cool atoms to almost absolute zero as advertised using lasers and magnets. So I'm a PhD student at the physics department in Cambridge in the group of Ulrich Schneider, where we do many-body quantum dynamics. So the idea of what we are trying to do is basically that there are these materials, for example, superconductors, which exist, but we kind of don't really understand how they work. And this means that it's kind of difficult for us to design better versions of them. And there is, some degree of trial and error involved because we don't really understand the underlying physics very well. This is not because we don't know what the kind of Hamiltonian, so the physical model that describes these materials is, but it's more that doing any computer simulations becomes very difficult because the computational time scales exponentially with the number of particles, the number of atoms that you have in the material that you're simulating. And experiments on real materials, as I was already saying, are kind of difficult because we don't understand them very well. And also, you might also always have some impurities in your material. So it's not always very clear whether the effects that you're seeing are due to the impurities or whether there is actually, or whether they come from what you think they're coming from. So to address these questions, in the last kind of 20, 25 years, a new field has emerged, which is the field of quantum simulation. And essentially the idea of what we're trying to do is we want to create module experiments which display the same physics, which means they're governed by the same Hamiltonian as these real materials. But we want to implement these module experiments in such a way that we have a very high degree of control over all the parameters in such a way that we can precisely tune or vary any of the parameters and see how the behavior changes. So in this kind of context, one of the avenues that has been pursued is that of using ultra-cold atoms and put these ultra-cold atoms into optical lattices, which are basically made by interfering laser beams. This is essentially what Georgia was describing in one of the previous talks. She gave a very good introduction, so I won't go into too many details here. So the idea is if we want to simulate a condensed matter system, for example, we need a periodic structure, which indeed is given by these interfering laser beams. And then we usually care about the electronic properties of the material. And so instead of using electrons, we will use an ultra-cold gas of atoms. And this will allow us to achieve a very high degree of control. Now, the question is, how do we actually make this gas of ultra-cold atoms? And how do we get it to behave quantum mechanically? After all, you might remember from your undergraduate that when we talk about gases, we usually say there's the ideal gas law. So we can simulate the gas just using the laws of classical mechanics. But we also know from quantum mechanics that in principle particles are waves. So where's the catch? Why does a gas at room temperature not behave in a quantum way? And how can we make it behave in a quantum way? So it turns out the catch is that this quantum mechanical behavior only really appears when your gas of atoms is very cold and very dense. So this is because the size of the quantum mechanical wave packet will increase as you lower temperature. So at room temperature, for most things, these wave packets are so small compared to the distance between particles that what happens is basically just governed by classical mechanics, and so it's somewhat boring. However, when you start lowering the temperature, then these wave packets will start becoming bigger, especially compared to the separation between the particles. And then at this point, you can imagine these particles are just kind of little ripples that are traveling through, say, a medium like water. But these ripples are very small compared to their separation, so they mostly still travel classically, and you can sort of keep track of which ripple is which. And they will only really interfere or behave quantum mechanically when they come next to each other. What is then even more interesting is if we go to even lower temperature and higher density, then we get to this situation where the size of the wave packets becomes comparable, if not bigger, to the separation between the particles. And then at this point, if you think again about these ripples on a surface of water or something, it doesn't really make sense to talk about particles and say this particle here and this particle here, because it's just one overall wave pattern where you can't really distinguish one particle from the other. And this is when the quantum behavior of the particles becomes very important. And for example, it becomes important whether these particles are fermions or bosons. So this is the kind of regime that we want to achieve where all these interesting things happen. By the way, this is also how electrons look, as it were, in a material. So we have these electron waves which are delocalized over the entire material. So maybe you can already see that this is kind of an equivalent thing that we could do with our atoms. Okay, so we've established that cold atoms are interesting. Now, how do we actually cool them? So in order to understand that, let's just have a quick recap of what temperature is. So from the laws of thermodynamics, we know that temperature is a collective property of an ensemble of particles, and it tells us something about the range of kinetic energies that we have in our ensemble. So high temperature means that we have the particles going in all sorts of directions with a very large range of speeds and kinetic energies. And therefore, cooling the particles basically means that we want to slow all these particles down so that they're all, for example, at rest. Okay, so to cool atoms, there are essentially two main techniques. One is laser cooling and one is evaporative cooling. So let's look into each one of these in some more detail. So laser cooling essentially exploits the fact that photons have a finite amount of momentum. So if you imagine an atom here, which is traveling, say, to the left, and it absorbs a photon that is traveling to the right, then when the photon is absorbed and the valence electron inside the atom will be excited, and the momentum of the atom will be reduced in case they're traveling in opposite directions. So this will have slowed down the atom a little bit. Now, a short time later, this photon will be re-emitted spontaneously. But this will happen in a random direction. So on average, this will not change the momentum of the atom. So overall, we saw that with this kind of process, we were able to slow down the atom. However, you might also be thinking very rightfully that there is a problem, which is that the atoms actually move in all directions. So what do we do with the laser beam? Which direction should we send it in from? And how could this possibly work? Because it seems like if we send in some photons, say, from the left, then we slow down some atoms, but we also speed up some other atoms. So this looks like it might not work. However, luckily, the Doppler effect comes to our help. Now, you can imagine that these atoms are essentially like little antennas that only listen to a particular frequency, that is the transition frequency. This is very similar to what Professor Binney was talking about in his talk this morning. So if you essentially imagine you have these, you have this atom, and now you send in some photons which have a frequency which is slightly below the resonant frequency. Then if the atom is at rest, then the atom will not be able to absorb the photon because it's at the wrong frequency. However, now if the atom is moving, which we can see by transforming into the reference frame of the atom as indicated by this vector v, then what we see is that if the atom is traveling towards the photon, then there's this Doppler shift which increases the frequency of the photon. Essentially the same thing as if an ambulance is approaching you and you hear a higher pitch than when it's going away from you. And so because our original photons were slightly below the resonant frequency, then now they will be shifted into resonance, and the atom will be able to absorb the photon. On the other hand, if the atom is traveling away from the photon, then the frequency will be shifted down, and therefore it will be going down out of resonance. And so by this scheme, basically we see that photons are always preferentially absorbed against the direction of motion, which slows down the atoms and therefore results in cooling. Then, okay, so unfortunately this technique doesn't allow us to get quite as low as we need for all the interesting things to happen, at least in some atoms. So we also have this evaporative cooling scheme, which essentially works the same way as when you have a cup of tea. And so it will cool down because the most energetic atoms have enough energy to escape your cup of tea and carry away more than the average energy. So the energy that is left will be slightly lower. And then what we can also do is reduce the trap depth, which allows more and more atoms to escape. This would be equivalent to taking a cup of tea to higher altitudes where the boiling point of water is lower. So at the end of this, we will have lost a lot of atoms, but the ones that we are left with will be a lot cooler. So following all this procedure, we can cool the atoms down to quantum degeneracy, which means we can go first to about 100 microkelvin and then even further to 100 nanokelvin. And then once we have these degenerate states, which could either be a Bose-Einstein condensate or a degenerate Fermi gas, then we're good to go and we can do our quantum simulation experiments. So just to conclude, this is what a cold atoms lab looks like in practice. We have a vacuum chamber and we send in a whole bunch of lasers. And then the way we probe the system is by basically taking pictures of the atoms. And we can also see, what you see in this picture is we can diffract the atoms. So this really shows the kind of matter wave character of these particles, diffract the atoms using laser beams. So let me thank the organizers again and my team for helping with this work, and thanks everyone for listening.
Thank you very much, Luca, for an interesting talk. If anyone has any questions, again, either raise your hand or type them in the chat.
We have a question from the YouTube live stream. So William asked, what is the limiting factor for the temperature you can reach using laser cooling?
Okay, so there are essentially two scales. One is, essentially they have to do with how accurate or how specific the frequency of the laser has to be relative to the transition energy. So that is given essentially by the line width of the atomic transition. So that is one first scale, which is called the Doppler scale. And that is, for example, for rubidium, which is one of the most common atoms, that would be somewhere above, say, about 150 microkelvin. And then it turns out you can actually do slightly better. And the kind of ultimate limit for laser cooling is essentially the momentum of a single photon. So if you imagine you're almost at rest, now the best that you can do to slow down a bit more is to absorb one photon. But then that means that it would be very difficult to have less than that amount of momentum on average. And so that that kind of temperature scale is probably about several hundred nanokelvin for rubidium. So in principle, you could get a lot lower, but it becomes very difficult. And then if you have any kind of uncancelled magnetic field in your setup, then it kind of becomes slightly impossible to go that low. You can play some more complicated tricks using kind of narrower line width transitions, if you like, and people do this indeed, but it does become more complicated.
Okay, thank you very much. Any other questions that anyone has? If not, I guess we can move on to our next talk. So that will be Alex speaking on the entire Messier Catalogue in under 10 minutes. So Alex, if you'd like to take over and share your screen.
Can do, yes. Thank you very much. Can you see that okay and hear me okay? Brilliant. Okay, yeah, so my talk is going to be a little bit different because I applied for about 10 internships or so over the summer, and they all rejected me. So in lieu of talking about any work that I've done over the summer, I thought I'd tell you a little bit about the Messier Catalogue. And it's a bit long, so apologies if I overrun a bit, and I'm probably going to talk quite quickly as well. So hang on one sec. Yeah, okay, so right, I guess we can get started. So Charles Messier was interested in spotting comets, and comets look like fuzzy blobs which move along through the constellations. But there were some other fuzzy blobs which did not move, and they stayed fixed, and they were kind of getting in the way. So along with his assistant Michon, Messier decided to catalogue these, make a big list to exclude them from the search. Now, it turns out that there are quite a lot of different types of object which look like a fuzzy blob in the night sky. There's some types of star clusters. So there's globular clusters, which tend to be spherical and have lots of very old stars. And then there's open clusters, which are a bit more randomly distributed and tend to have younger stars. A couple of types of nebulae as well, diffuse nebulae, regions of gas and dust and rich regions of star formation, and planetary nebulae, which have nothing to do with planets at all. They just kind of look like them sometimes. And this is what happens when a relatively young star dies and it exhales away its outer layers. When a bigger star dies, of course, it goes supernova and leaves behind some of these slightly more ragged remains here, such as this one. And all the things I've mentioned so far are found within our own galaxy, within the Milky Way. But of course, lots of Messier's catalogue does actually have galaxies other than our own. So the Messier catalogue has 110 objects in it. I intend on showing you all of them. So this is probably going to go incredibly badly. But hopefully this is just a bit of comic relief and isn't intended to be very serious at all. So hopefully you enjoy it. I don't have very long to tell you about each one, but if nothing else, this is just a great excuse to see some of the incredible images that Hubble and co have sent back of some of these very, very beautiful objects in many cases. So 110 objects. Let's go. M1 is the Crab Nebula, a great one to start with, a supernova remnant from a supernova that exploded in 1054 as observed by Chinese and Islamic astronomers. M2, a globular cluster, you can see it's quite spherical, 13 billion years old, this one, given the universe itself is only about 13.7. This is a really, really old thing. M3 was discovered by Messier himself, unlike the first two. M4 is the closest to Earth. M5 is a bit boring, but M6 is the butterfly cluster. You can see this is an open cluster, and so the stars are a bit more spread out. And also the outline kind of looks a bit like a butterfly, like this one. And I'll have a few more props to help me as I go along. M7, the Ptolemy cluster. Now, if I overlay this image on top, this was the first ever image taken by the New Horizons space probe. It was used to calibrate its camera as it went on to send back all those amazing pictures of Pluto. M8 is the Lagoon Nebula, very, very beautiful. Also contains a space tornado, which is quite cool. M9, another globular, as is M10. M11 is the Wild Duck cluster. And honestly, I have no idea why they thought this looked like a duck at all. M12 is a globular, so is M13. M13 is interesting because it was the target of the Arecibo message in 1974. You may recognize this image. It's a bit of a waste, though, because there's almost definitely no planets whatsoever in any globular clusters anywhere, but it got Carl Sagan some good publicity, so, you know, maybe worth it. M14, a couple more globulars, M15. M16 is the beautiful Eagle Nebula. The interesting thing about this one is if we zoom in to this red region here, we find the Pillars of Creation photo taken in 1995, which obviously inspired so many people about astronomy. M17, the nebula of many names, but it doesn't, if you ask me, it doesn't really look like any of them, but it still looks kind of pretty. M18, a nice open cluster. M19, a globular. M20, this is the Trifid Nebula because it has this sort of Mercedes logo thing going on. If we zoom in on this blue region here, then we get this weird two-horned gas monster, which is quite cool, but I don't really know how that works. M21, a few clusters on the way now. 22, a globular, contains not one, but two black holes. 23, a nice open cluster. This isn't even a cluster. This is just what happens when you look towards the center of the Milky Way and there are loads of stars there. And Messier thought, oh, we'll include that. Why not? M25 and 26 are both open clusters. M27 is the first planetary nebula that was ever discovered. It was by Messier himself in 1764. And based on the rate at which this bubble is expanding, we know that it's just under 10,000 years old, which is quite a cool bit of science. A few more clusters, M28, M29 for some reason is called the cooling tower. Again, no, you really have to use your imagination with some of these. M30 currently collapsing. But M31 is a very interesting one because it's the nearest galaxy to the Milky Way. It's the Andromeda, and it's the furthest object visible to the naked eye, but it's getting closer. And in about 5 billion years, it's going to collide with the Milky Way around the same time that the sun explodes. 32 used to be a big spiral galaxy, but it's actually now orbiting Andromeda. And in the meantime, Andromeda ripped away its disk. So now it's just a sad little blob. M33 is the Triangulum galaxy, and you might want to cover your ears for this bit because I have a triangle for that. It's also a bit behind the Andromeda, and it's converging on the Milky Way as well. So it's probably going to be actually a three-way collision. 34, a few more open clusters, 35, 36, 37, and 38 is only interesting because it has a very cute name. And I've got a starfish here whose name is Angelo to demonstrate this, although you'd be kind of hard-pressed to find a starfish anywhere in there. M39, M40 is just two random stars that just happen to be sort of in a line. In fact, the one on the left is closer to Earth than it is to the one on the right in space. But Messier just decided to include that anyway, I guess. M41 is not very interesting, but M42 is the gorgeous Orion Nebula, my personal favorite in the whole list. It's located in the night sky in Orion's sword or Orion's dick, depending on how you view that. It's a region of not only star formation, but also planet formation. And if you look very carefully here, these are protoplanetary disks where planets are being born. If we look in the top left here in this square and zoom in, we get M43, which is de Mairon's Nebula, which is in the process of colliding with M42. 44, planets have also been seen orbiting around some of these stars in this open cluster. 45 is a very easy one. It's the brightest and the nearest Messier object to the Earth, easily visible to the naked eye on a winter's night. Also called the Seven Sisters, so you know what's going on. These ones on the right are the sisters, carefully watched over by the two parents on the left. It's soon to become the Six Sisters, sadly, because this bright one over here is going to quietly die at some point soon. 46, some more open clusters now. 47 is quite a pretty one. 48, nothing particular. M49, this is the first galaxy to be discovered outside of our local galaxy cluster. This is a member of the Virgo cluster nearby. So this is sort of a cousin of the Milky Way, this galaxy. M50 is a bit boring, but M51 is the beautiful Whirlpool galaxy. There's this sort of parasitic galaxy over here in the top right, which is winding the Whirlpool galaxy into this beautiful spiral, which just so happens to be face onto the Earth. And this gorgeous specimen was discovered by Messier himself, again, as was M52, but this just looks rubbish in comparison. 53, a few more globulars now, 54, and 55, which has the romantic name of the Summer Rose star. 56 is also a bit boring, and 57 is the Ring Nebula, and this is an absolutely beautiful specimen. It's from an explosion that was about 7,000 years ago, and you can see this little white dwarf at the center, which is the remains of that star. 58 also in the Virgo cluster, another cousin of the Milky Way, as are M59 and M60. There's this totally unrelated spiral galaxy for M60, which is actually 6 million light years behind it. And it kind of looks a lot prettier than M60 itself, to be honest. M61's forming lots of young stars very, very quickly. And so there's this band of blue in here. This type of galaxy is sometimes called a starburst galaxy because it's bursting so many stars into existence. M62 is boring, but 63 is the lovely sunflower galaxy. Really pretty lanes of dust here forming these lovely spiral. Likewise, M64 called the Black Eye or the Sleeping Beauty galaxy. I think the second name seems a bit nicer. The weird one about this is that it has two disks which are rotating in opposite directions, and nobody really, the center stars are going in the opposite direction to the outside, and I'd love to see what James Binney would have liked to say about that. M65, the spiral arms here are a little bit distorted, and that's because it is interacting with M66, which also looks very unhappy in its spiral arms. 67, the funny thing about this is all the stars are very similar to the sun in terms of their age and their composition. People once thought that the sun might have been born in this cluster and then been kicked out somehow to where it is now, until this paper came out, which says the sun was not born in M67, which in scientific terms is incredibly blunt. I love it. 68, a few more globulars now. 69 is quite a nice one. 70, the comet Hale-Bopp was discovered quite close to this one, so it's a good thing Messier had his catalogue, or we might not have discovered it properly. 71 is a bit of a rubbish globular cluster. Likewise, 72. Again, 73, this is just 4 random stars this time. It was only in 2002, though, actually, that we discovered this was not actually an open cluster. It's just 4 totally unrelated stars that happen to appear close to each other. 74, the incredible phantom galaxy. These ones where they're face on and you get these beautiful spirals are sometimes called grand design spirals because, I mean, they just look incredible. 75 is very bright because it's very centrally concentrated. 76, the little dumbbell, and annoyingly Hubble's camera has cut off the other dumbbell in this, but yeah, you can only see one lobe, unfortunately, in the Hubble photo. And 77 is relatively dull. 78, the funny thing about this is there's a little star in here which is illuminating the back wall of this cavity that it's in, and it's just making the star itself look way bigger than it is. It's sort of doing the thing where it's trying to scare off a tiger by making itself look big. So 79, the Milky Way might have stolen this from another galaxy because it's nowhere near the rest of the Milky Way's globulars. M80 is very, very dense. There's at least 2 black holes near its core. 81, again, there's some distortion with the spiral arms, and that's because it's interacting with M82, the cigar galaxy. Another starburst galaxy, lots of stars being born here, but also lots of stars dying, and there's lots of supernovae in this one, such as this. The gas given out by those supernovae tends to get funneled out of the sides, which is what you're seeing in the red smudge there. 83, the southern pinwheel, very bright if you're in the southern hemisphere. You can see this with binoculars. 84, there's this silhouette in front of it, which is due to a random lane of dust in between us and the galaxy. In the radio wavelength, it looks like this, because there's a billion solar mass black hole right in the middle of it, which is trying to start some rotation going there. 85 is a bit featureless, as is 86, but M87, this is an absolute monster of a galaxy. This absolutely dominates our local universe. It has trillions of stars. It's 4 times the mass of the Milky Way. And if you look closely, you might be able to see this blue jet coming out of the middle. If we look in radio wavelengths, it looks like this. Now, if we zoom in right in the middle of that and build $50 million worth of telescopes all around the world, then we get an image that looks like this, because the famous black hole image was the black hole at the center of the incredibly massive galaxy M87. M88 is actually orbiting M87. That's how big M87 is, as is M89. M90, there's not very much star formation going on here, and so sometimes it's not described as a starburst galaxy, but the opposite, which is an anemic galaxy. There's some interesting terminology that astronomers have for these things. 91, Messier wrote down the wrong coordinates for this, so nobody knew where it was until 1969, so it was completely lost for about 200 years. Good job, Messier. 92, back within the Milky Way. M92, a globular. 93, an open one, discovered by Caroline Herschel, incidentally, this one. M94, the lovely cat's eye galaxy. Now, 25% of the mass of this is in this glittery outer spiral here, which gives it a nice cat's eye effect. 95 is the faintest one in the entire catalogue, making it incredibly difficult for anyone to find. 96, a lovely sort of maelstrom of dust here. Honestly, some of these pictures, you really could look at them for hours. 97 is the lovely Owl Nebula. I would have named this the Bubble Nebula, personally. Oh, I've got an owl as well. Yeah, based on the rate that this is expanding, it's about 8,000 years old, this one. 98, back to the galaxies, a lovely disk here. 99, the spiral arms are going crazy. We're nearly at the end now. M100, there's a supernova happening in this galaxy, and it's here. It's incredibly bright, as you can see. 101, the Pinwheel Galaxy. I think you'll agree this is very aptly named. This is one of the first spiral galaxies ever to be discovered. M102 is very weird. It's quite hard to tell what's going on because it's completely edge on from our point of view. M103 is not very interesting other than the fact that it has this weird red member here. M104 is the Sombrero Galaxy, another one which is quite side-on, but unlike the Spindle Galaxy, there's a tiny bit angle, so you get a little peek inside, which makes it look spectacular, both invisible and in infrared. M105, almost there, a nice elliptical one. M106 has an enormous quasar at the center. 107 is 12.8 billion years old, again, going quite right the way back to the start of the Milky Way. M108 is a very dodgy spiral galaxy. M109 has this nice bar in the middle called a barred spiral galaxy. This one, I think James Binney mentioned that as well. And finally, M110 is a satellite of the Andromeda Galaxy, which I'm sure you will have all remembered was M31. And that is it. That is the entire Messier catalogue. I've overrun a bit, so very sorry for that. But hopefully, you enjoyed that. Thank you very much. If you have any questions, please say. Thank you.
Thank you very much, Alex. That was incredibly entertaining. If anyone else has any comments or questions to ask.
I forget if you said anything about
Oscar, I think it was like quite muffled.
Can you hear me?
Yeah,
Yeah,
yes.
that's better.
Yeah, okay. No, I just changed microphone. Okay, amazing. I forget if you said, which one is your favorite?
That would be, hang on, I'll try and get it back up. Sorry, I shouldn't.
Please.
Really yes, so my favorite, very good question, is M41, M42, sorry.
M42.
The Orion Nebula, this one.
Is that because of Orion's dick?
Partly that, yeah. But partly, it's just, it's crazy that we're able to see so many planets being born in the same, in the same region of the sky. I should probably cover up that the XKCD there, maybe. Oh yeah, this is going on YouTube, isn't it? Whoops. Oh well.
It's being live streamed right now.
Brilliant. Okay. But yeah, it's just really pretty.
No, I completely agree. I can see that. No.
I know I was going quite fast, but did you find a favorite out of any of them?
Oh, I must admit, I don't recall which one is which. What's that?
I like the bubble one.
Yeah,
it's very pretty.
Nice, yeah.
The bubble one was very cute. Yeah.
And the one that's called an owl. Honestly, if we're given in the sort of same vein as the XKCD, I think there was the cigar galaxy or something. I misread that as sugar daddy.
Yeah, I tried to use a different font for all of them, and that was a particularly unreadable font.
The first word.
Yeah, no, I can see that.
Yeah, I'm concerned for you, Alma, but I
think it says more about you than it says about the font.
Yeah.
Oh yeah, that's true. But we don't talk about it.
No.
I guess if we have no more questions, we can move on to the next talk.
Yeah, that's me. I can't match this. Like Alex.
Move on very swiftly.
There's just one comment on the YouTube live stream where Saklan said that they like the Owl Nebula. So
yeah.
Oh,
yeah.
Right. Yeah.
I feel like if you gave it eyes, it could be like full on the star of its own movie, like an animated movie. Like it's adorable.
Yeah. Well, there are lots of old pictures of it where it looks a bit more like an owl. And that's because people identified two sort of lobes in it, which looked like two big eyes, and so that's where the name came from. So yeah, do look up some of the old photos. Well, really drawings of it, because it was in like the 1800s, where it does look a bit more like an owl.
Mm-hmm.
Yeah.
So if you, Oscar, if you'd like to take over,
sure. Let's
talk.
See. How can I? I can't see anywhere. Oh, share screen. I'm just actually blind. Yes, share.
And I will mute myself.
Can you all see? Yeah, amazing. So sorry to interrupt this session of fun. I have prepared something I worked on last summer in the year of the plague, 2020, down in Germany, where I miraculously managed to actually travel internationally with Francesco Piazza and David Lutz at the Max Planck Institute for the Physics of Complex Systems. And what we're going to talk about is basically how quantum computers doesn't work. You can see my Discord notifications, presumably, or is that just me? Can you see my Discord notifications? I should quit Discord. Oops, never mind that. I have a D&D session tonight, so that's probably that. But anyway, so we're going to talk about how IBM's quantum computers don't work and trying to quantify that. And particularly, we're going to talk about how operators decay in quantum computers. And my work was partly experimental, partly theoretical with modeling, and resulted in this paper in Physical Review Research, which I go recommend you read and more importantly, cite. You can find a lot more details there. But I'm going to take a slightly different approach to what they describe here, or what's described in the paper, and try and start from the quantum computing perspective rather than many-body physics, which is what we did in practice. Particularly, what is a quantum computer? Well, a quantum computer is a machine, a programmable machine that can implement unitary transformation. It's a big linear algebra machine, essentially. And the whole goal of what the entire maths department does is basically trying to figure out, if we have some basis gates, how can we combine them into making an arbitrary unitary transformation of a state. So this is what we have everyone in quantum algorithms working on, very roughly speaking. The only problem is when you actually try to do that in real life, it doesn't work. It absolutely doesn't work, because the base building blocks you build your unitary transformation of, these gates, they have to be incredibly precisely implemented in real life. So in practice, what you do is you have these qubits that are built up of like superconducting circuits, for example. That's the most common. And then you hit them with some microwave radiation. And then you pray you've gotten the exact timing right and the exact amplitude of the radiation right, so you can implement your gate. But of course, you're always going to get it slightly wrong. So what that's going to do is it's going to introduce some error. And that error is not necessarily going to be predictable. So in practice, what happens in the real quantum computer is that we don't get a unitary time evolution. We get some random and non-unitary evolution that's close to the true revolution if there is little noise. So some mathematician could probably find some measure in which they're close to each other, but we don't really care. Like the intuitive idea is true. If there's no noise, they're the same. If there's little noise, they should be close. But this, of course, presents a problem, because if the noise is big, they might not be close. And what we measure isn't what the maths department predicts. And then we can't use it to, like, I don't know, break encryption and make a lot of money. So we could be interested in studying how much they differ. And particularly where they differ is when we begin to measure stuff. So we will always in quantum mechanics be measuring the expectation value of operators, or measurements of basically expectation values. And they're not going to be what we predict, but can we be more precise? And that's what we're going to do in this paper. Specifically, we're going to look at what operators are good to measure, what are bad. And we're not going to need to know basically anything about how they practically implement the quantum computer, just some pretty reasonable assumptions. Specifically, when we talked about like generic unitary rotations, transformations, whatever, we didn't really think about the specifics of how the quantum computer being built up of qubits. And that's important because when you act with the individual gates, they can only act on a single qubit or two neighboring qubits at the same time. And furthermore, when we have the errors, they're always acquired at the individual gate level. So errors can be correlated. For example, if you have a gate that's acting on two qubits at the same time, it might mess up both qubits at the time, but mess them up in a coherent way. And that's actually a really important mechanism. But because there are no native 3-qubit gates that act on 3 qubits, for example, time, you'll never have 3 qubits that at a given instant will be coherently error prone. And this kind of allows us to build up some sort of geometry almost of the quantum computer where errors kind of propagate out, and allows us to actually do some relatively generic modeling. So what we do in terms of modeling is we try to map it onto time evolution. We say circuit, it's basically time evolution. We have layers of the base gates and they go to some depth t, which we can think of as a time. And if we have an operator, it's going to be completely useless after some characteristic timescales. Turns out that basically always decay exponentially. And if we assume that each individual layer takes an infinitesimal amount of time, which isn't true, but it's a good modeling assumption because then the theoreticians, they can actually calculate stuff. Then it turns out that the operators which we measure, the decay timescales can be predicted to follow this, this polynomial curve. In particular, if they act on k qubits out of L, then the characteristic timescale by which they decay, tau k, is proportional to these two terms, which corresponds to how much decay happens coherently when you act on 2 qubits, and how much decay happens when you act on a gate with 1 qubit. These are the lambda 1 and lambda 2 parameters. But in practice, this is just a polynomial fit. Now, to implement this in practice, what we basically did was, well, the modeling kind of ignored all that the quantum computer was meant to do and only looked at how it was meant to fail, like how fast these operators decay into noise. So we need to find a circuit that the mathematician would say, this does nothing. This is useless, this does nothing. But for our purposes, it's essential. So we build up a circuit by essentially creating a random circuit of layers. So each layer here corresponds to a time step, and each qubit is rotated by some random amount. We don't really care. And then we pick 2 random qubits and we act on them with a CNOT gate. And we built up T layers of that, and then we undo the whole thing. And it turns out that this induces exactly both this 2-body noise and this 1-body noise. And when we try to measure the expectation values of operators, so here I have a few thousand expectation values that we've all been able to fit exponential curves to. Well, I say fit exponential curves. If you look at an individual time trace, my lab demonstrator would probably say this isn't exponential at all, but it's close enough that we can extract some sort of data. And then we order by the number of qubits they act on. We get this beautiful agreement with the theory, which is the blue curve, and the mean center of each of these. So these are decay. Each individual line is kind of a decay rate. And then the orange dots are kind of the center for each cluster. We get almost perfect agreement here. And this was very, very interesting because, as you can see, perhaps quite unintuitively, there's this backward bending where like operators that act on more qubits, so you would think are more complicated, are more prone to noise, can actually decay slower than ones that are less complicated. This was an interesting theoretical prediction that we were interested to see. Can we actually see this in the real quantum computer? And that's, I think, everything. Thank you very much. Do you have any questions?
Thank you very much. Yeah, again, as usual, either raise your hand or type in the chat if you have any questions. And I guess if someone can check the YouTube live stream as well, if there are any questions there.
I mean, I will say in practice, this sounds very, very neat. In practice, this involves like 3 months of just giving things to IBM, asking them to run it and getting out like basically pure noise. And then like the week before I was meant to end my internship, we managed to figure out like a configuration of like the circuit thing that actually gave like reasonable predictions. So like it was an extremely last minute thing. So lots and lots of stress, lots and lots of fun. If you're interested in many-body physics, they have an internship program that they run each summer. I can recommend you apply to. They're super nice down in Germany.
Okay, I guess if like there are no other questions or comments to be made or anything, are we happy to leave it off there?
Yeah.
Sure.
stop live streaming anytime now then?
Yeah.
Okay, well, everyone, thank you everyone for speaking at the Varsity Sci event today. It's been a really interesting series of talks. Yeah, so thank you very much, everyone.
Thank you.
Thank you.
Thank you.
Great.